Let's get a little more into kinetic molecular theory and particularly talk about speed distribution of gas molecules as it relates to Graham's law and the behavior of non-ideal gases. The kinetic molecular theory of gases, in short, gases are point-like particles moving about at random, very high speeds. The molecules themselves are spaced in the gas very far apart relative to their size. Gas molecules neither attract nor repel each other. Collisions of the gas particles themselves are elastic. That means when they run into each other into the walls, there is no loss of energy. And last, the average kinetic energy of gas particles, molecules, is proportional to the Kelvin temperature of the gas. This is a molecular speed distribution apparatus. As you can see, we have rotating disks here, and we have an oven that heats gases, passes through a couple of collimator slits, and then this chopper will just piece off a parcel, a little bitty part of the gases. Now, they're still moving at different speeds, so the fast ones will hit first, and the slow ones will hit last. And you can measure the angle between the incident of the when they hit the chopper and the place where they hit the disc, and that, of course, with the length gives you the distance that they're traveling in a given, say, millisecond, and therefore the molecular speed. The detector then will count the number of molecules with each packet. As we vary the speed of rotation, we can then get a count of the number of molecules at any given velocity. And of course we can then plot that against the velocity. When we do that, we get a distribution like this. At 200 Kelvin, we have a distribution that's kind of tall and clustered around slower speeds. When we heat the gas to 600 Kelvin, it spreads out and we get more and more molecules moving at higher speeds. And at 1000 Kelvin, we have even more molecules moving at higher speeds. The area under each of these curves has to be the same because the number of molecules is going to be the same the way we run the experiment. Let's talk about those speeds and molar masses. Let's suppose one gas has a mass of 10 and the other has a mass of 40. What's the relationship between their velocities? Well, we know at the same temperature the average kinetic energy of two gases has got to be the same. Kinetic energy of the first gas has to equal the kinetic energy of the second. But kinetic energy itself is 1/2 mv squared. Therefore, 1/2 times the mass of the first molecule times the square of the velocity of the first molecule is equal to 1/2 times the mass of the second molecule times the square of the velocity of the second molecule. Now, if that's true, then we can also say the square root of m1 times the square of the velocity 1 is equal to the square root of m2 times the velocity squared. And we can then say that the square root of m1 times v1 is equal to the square root of m2 times v2. Then, if we arrange the terms in a different way, dividing both sides by v1, for instance, and then dividing both sides by m2, we get v2 divided by v1 equals the square root of m1 divided by the square root of m2. If we then put the square root of 10 on top, the square root of 40 on the bottom, we divide those out, we get a ratio of 0.5. What that means is that this gas that is 4 times more massive than that is half as fast as that. And that, of course, relates to the fact that the velocities are squared in the kinetic energy equation. Here are some average speeds of molecules at 25 degrees Celsius. In hydrogen and helium, water vapor, nitrogen, oxygen, and carbon dioxide. And as you can see, as the molecular mass is increasing, the average speed is decreasing, but not linearly. This is 22 times more massive than the hydrogen, but it is not 22 times slower. The speed here 1960, the speed here 415 meters per second. Now Graham's law can talk about diffusion and effusion of gases. Diffusion is the mixing of different gases by molecular motion as they collide. We take gas 1 and gas 2, put them side by side, and then open a small slit between them and see how fast they diffuse into each other. Effusion relates to the escape of a gas through a pinhole, like this, into a vacuum without molecular collision. This is a very small hole, and the gas molecules have to be moving at exactly the right velocity and mostly direction in order to get through the pinhole. We can measure the rate of effusion. Graham's law tells us that the rate is some constant times the inverse of the molar mass. That fits into what we now know also about the kinetic energies being proportional to the square of the velocities. So, in Graham's law, for both effusion and diffusion, the rate for one gas divided by the rate for the other is equal to the square root of the molar mass of the second gas divided by the square root of the molar mass of the first gas. Again, the gases have to be at the same temperature and pressure, or this doesn't work. So, you can determine how much faster helium atoms at a molar mass of 4 move than carbon dioxide molecules at the same temperature. And carbon dioxide, of course, has a molar mass of 44. And then you can determine the molar mass and identity of a gas that moves 4.67 times as fast as carbon dioxide. Go ahead and turn off the video and solve the problem and then look at the answer. Carbon dioxide is 11 times more massive than helium, so we take the square root of 11, and that's 3.32. Helium must be 3.32 times faster to diffuse or effuse than carbon dioxide. If we square the 4.67, we get 21.8. 44 divided by 20.1.8 is 2.01. So the molar mass of the faster gas is 2.01, and that's hydrogen H2. And yes, that's a classic run-on sentence. Now, real gases don't behave quite like ideal gases. The volume of a real gas is larger than predicted by the ideal gas law. Why is that? Well, the molecules have a volume. At lower pressure, it really doesn't matter because the volume of the gas particles is truly negligible compared to the total volume. But when we increase the pressure, the volume of the gas particles becomes a more significant part of the total volume. So the volume of a real gas at high pressure is larger than what we would have predicted from the ideal gas law. The other issue is that as particles get closer together because of increased pressure, the real fact is that the molecules do attract each other. We know that because all gases at some temperature and pressure will liquefy. So there is a force of attraction between the molecules. The speed of the molecules, of course, is the same if the temperature is the same. But if you're compressing these together, the frequency of close interactions is higher. So under what conditions do real gases behave most ideally? This is a frequently asked test question. To reduce the effect of the volume of molecules, we have to make the molecules very far from each other. So gases will behave most ideally if the total volume is huge relative to the molecular volume, so at low pressures. When the intermolecular forces are negligible, the molecules have to be moving very fast. If they're moving very slowly, the intermolecular forces of attraction can bring them close together and make them clump. Well, we need to therefore make the molecules move fast, so ideal behavior occurs at high temperatures. Low pressure, high temperature, those are the factors that give us mostly ideal gas behavior.